In this example, we have an open loop control system where the plant is given in the form of a transfer function with 10 over s plus 1 and the open loop controller which is designed by someone in the form of s plus 1 over s plus 10. And the disturbance is being added to the output of the controller this time. We want to compute the time response of c of t for t bigger than or equal to 0, assuming that initially it was equal to 0 and the reference input is equal to 3 times step of t. For part A, we assume that the disturbance is equal to 0 and therefore the output for the system could be obtained in this way. C of S will be equal to the transfer function of the controller times the transfer function of the plant times the input, which is R of S. And we know that R of S is equal to 3 over S. Therefore, C of S will be equal to, if I just simplify this, C of S will be equal to 10 over S plus 10 times 3 over S, or 30 over S times S plus 10, and you can rewrite it in the form of 3 and minus 3. 3 over S plus minus 3 over S plus 10. If I want to obtain the time domain equivalent for the output, C of t will be equal to 3 times U of t, assuming that U is indeed the step, minus 3 times E2 minus 10 times t times U of t. And if you want to find out the steady state value of the output, we will get 3 times 1 minus E2 minus 10t. E2 minus 10 will be equal to 0, and therefore the output will be equal to 3. And which is the same as the steady state value for the reference, and therefore the steady state error will be equal to 0. Now in part B, we want to compute the time response, keeping the same assumptions, but this time we assume that the disturbance is present as well. So d of t is equal to du is equal to step of t, or ds is equal to 1 over s. Now the output cs will be equal to basically we can assume that it will be equal to r times gc, the controller, times gp, plus d times gp, because we can use the superposition principle. Yeah, so we will have s plus 1 over s plus 10 times 10 over s plus 1 times r, which is 3 over s, plus 10 over s plus 1 times d of s, which is basically 1 over s. And then c of s will be obtained as 30 over s times s plus 10, as before indeed. And then we will have plus 10 over s plus 1. And if I want to obtain the time domain equivalent, we will have, for the first part, we will have 3 times 1 minus E2 minus 10t times ut plus 10 times E2 minus t ut. And now if I want to find out the steady state value for c of t, we will get 3 from the first part over here, just a second, I forgot to multiply this with 1 over s, 10 over s plus 1 times 1 over s, and as a result what we have here should be corrected in this way. So we will get, I will rewrite this. So 30 over s times s plus 10, we know what we will get for that, plus s plus 1 is here, and we will have 10 here and minus 10 over here. So basically we will get 10 times 1 minus e2 minus t times ut for the second part, which comes from the disturbance. And the steady state value will be 3 plus 10, which will be equal to 13. And you can see that it is not equal to the reference value. The value that we get from the we got from the disturbance changed the steady state value for the output. So the open loop controller didn't work properly, let's say. Now for the last part, we want to compute the time response of C for t bigger than 0, keeping the assumptions that we had there in part A, so there will be no disturbance, but this time we will change the parameter on the numerator of GP from 10 to 11. And then we will see what happens to the steady state value of the output. So we know that for the output C of S, we will get S plus 1 over S plus 10. This comes from the controller. Times, this time 11 over S plus 1. This comes from the plant. And we have the 3 over S for R of S. C of S this time will become 33 over S times S plus 10. And we can rewrite it in this form. So C of t will be equal to 3.3 times 1 minus E2 minus 10t times U of t. And Ct, as t goes towards infinity, the steady state value of the output will be equal to 3.3. The steady state value for the reference was equal to 3. Now we have obtained the steady state value for the output, which is 3.3, or it is indeed 10% bigger than what we expect. Is this what you would expect from the sensitivity theory? Well, let's see whether it is the case or not. We know that for GP bar, we already had 10. Okay, so we have the GPS here, which is equal to 10 over S plus 1. GP at 0 will be equal to 10. Now the new GP bar is equal to 11, as the numerator has changed into 11. And therefore delta GP bar is equal to 11 minus 10, the new one minus the old one, which is equal to 1. Okay, so we have delta GP bar equal to 1 and GP bar itself was equal to 10. Now we can have a look at the L bar and delta L bar. L bar was equal to GC, the controller, times the GP. For GC we have 1 over 10. And for GP we have 10. So the L bar indeed initially was equal to 1. That's why without the disturbance we would have got the same steady state output as the reference. Now the new L1 new will be obtained as 1 over 10, which comes from the controller, and it is exactly the same as before, times 11. So it is 1.1. New L bar is equal to 1.1. The L bar is equal to the old or nominal one was equal to 1. So delta L bar will be equal to 1.1 minus 1, which is equal to 0.1. So I will write it here as well. L bar was equal to 1 and delta L bar is equal to 0.1. Now if you remember the sensitivity theory, that the sensitivity that we checked for the open loop system, and it was equal to 1. So delta L bar over L bar divided by delta GP bar over GP bar was equal to 1. Let's see if that's the case. Delta L bar is 0.1 over 1. Delta GP bar is equal to 1 over 10. And if you simplify it, you will get 1 as the result. So the sensitivity of the open loop system is equal to 1. That's why any fractional change in the process or plant will result in the fractional change in the DC gain of the loop, and that will appear at the steady state value of the output signal. Alright, so having gone through that example, here we have the general concept. If you want to obtain a high performance control system, we need a strong theoretical background. The theory of the open loop control is straightforward. Designing the open loop controller is easy, but the assumptions on the perfect model of the system and absence of the disturbance or having non-disturbances is never met. So we cannot simply use the open loop controllers. Instead, we want a theory that still works if things are different than expected. So there are disturbances and we don't have the nominal model of the system in the practice. And therefore, we will go towards using the feedback control. The feedback control will help us to obtain stable control systems which have desirable characteristics as we want. We'll go through this in the next lectures.